Okay, here's another lab that we could potentially do at Starbucks. It is a lab on the Faraday Lenz's law. Faraday Lenz's law basically states that a voltage will be set up in a loop of wire because a current is generated in the loop of wire due to the change in flux through the loop of wire. This is it's an abstract law, no question about it. But here we're gonna try and get some practical sense of this law and see what it actually looks like when we do it. Now there are three ways that we can change the magnetic flux through a loop of wire. The first will be to change the magnetic field, the strength of the magnetic field. The second would be to change the area, either shrink it or make it bigger. And the third way that you can do this is by changing the orientation of the area for which you're looking at the magnetic flux. Now I have here my IOLab device, and it is hanging from a spring, so it's going to behave like a torsion pendulum. And I want to take you on a tiny tour of this device. Remember, there are three ways that we can change magnetic flux: by changing the strength, by changing the area, or by changing the orientation of the area. This lab looks at the change in orientation of the area. So here's my IOLab device, and I have it hanging from a spring, so it's going to behave like a torsion pendulum. And I have a set of 6 coils of wire wrapped around the device, and of course that's copper wire. And it's connected to the high gain amplifier on the IOLab device. This will take very tiny signals and magnify them, which is what we want to do. So now let's take a look and see what it says. Remember, Faraday Lenz says that a current will be induced in a loop of wire so as to oppose the change in magnetic flux going through that loop of wire. So my loop of wire is here, my high gain amplifier is here. Where's the magnetic field coming from? Well, the magnetic field is going to come from the Earth. So let me go ahead and set up a little run here. I have my I/O software up and ready to go. And I'll just set a duration of about 15 seconds for my data run. And I'm going to use 2 sensors today. Actually, I should use 3, but I'll start with 3, and then I'll switch over. So here, the first sensor I'm going to use is the magnetometer, and that's going to measure the magnetic field. And I will use the gyroscope and the high gain amplifier. The high gain amplifier will measure millivolts. The gyroscope is going to measure the change in orientation of the device, and the magnetometer is going to measure the magnetic field, the magnetic flux going through the device. So here we go. We're ready to go. I'm going to try and keep this still. And I'm just going to take some data on the field of the Earth, just leaving this thing as is. So let me go ahead and click record. It's going to record for about 15 seconds. And as you can see, there's no signal in the high gain amplifier. There's no rotation going on with the device. Okay, let's just double check take a closer look at our curve. So here we are. It's very, very tiny vibrations in X and Y. We don't quite want that, so we might have to do this again. Here is the high gain antenna, or the high gain amplifier, and here's the magnetic field. And you can see there's a little tiny vibration in there. So let's try this again. And so I'll clear out everything. And I'm just going to try and keep this guy as still as I can. You know, it's bouncing around a little bit. There's air currents in the office and everything like that. Let's see if we can't shut that off. Okay, let's take another run. So here's my recording. There you see there's no change in magnetic field, but there is a magnetic field present, and that is the magnetic field of the Earth. So we're actually going to use the magnetic field of the Earth to make a measurement of Faraday's law. So here you see there's nothing going on with the gyroscope, there's nothing going on with the high gain antenna, and the magnetic field is pretty well constant. There's a little bit of noise, but that's acceptable. So now we're ready to actually take some data. So I'm going to go ahead and give this a spin 5 turns in a counterclockwise direction. So 1, 2, 3, 4, and 5. So I've done 5 turns, and I'll add the run to the device so we can actually take a measurement. And I'm going to go ahead and let it go and click record. Now, one thing you want to do when you do this experiment is you want to make sure there's no real vibrations going on in the vertical direction. So this is kind of a false run, and I'm not going to keep it. You should, when you do this lab, you should do it to try and keep no up and down motion going on at all. So I have this stopped, and let me go ahead and give it another 5 spins counterclockwise as I asked to do. 2, 3, 4, and 5. Okay, I'm going to leave it like this, and let's go ahead and reset because I'm not happy with that run. And I'm just going to hit record. And now, this is a good run because there's very little motion going on in the vertical direction. It's all going on about the y-axis. So here we are, and I'm just going to go ahead and stop. The recording has stopped. And what I want to look at, I'm not really interested in omega x and omega z. I am rotating about the y-axis. And you can see that from the diagram. So the axis of rotation is the y-axis. And so now what I'm going to do is, so I'm only interested in omega y. So here's omega x, omega z. We'll get rid of that. Now let's take a good look at first the magnetic field. We see that there's really not a lot of change in By. There's a few lumps there, but most of it takes place in x and z again. That's interesting, but now we're done with that. Let's take a look at the high gain amplifier, and this is where life gets really interesting. Because if I magnify this, which I'm going to do now, here is the curves. Now, what's interesting about this is, let's take a look in comparison with the angular motion. So here's when I'm at maximum, and you can see that my voltage is about 0.017. Here is where the device crosses 0, and you can see the voltage is about 0.007. That's about 0, or as close to 0 as you're going to get with this. And then if I go negative y, I'm actually at 0.01, so I'm actually decreasing back to 0. I see 0.007 again, and up at maximum I get 0.017. So here are my voltages, and you can see the shape of the curve, that it seems to, when I'm at maximum here, I am at maximum of the voltage. When I am at minimum, I am at minimum of the voltage. When I'm at 0, I'm very, very close. Let's get that to actually 0 on the y-axis. So let me try and find that. So when I cross the 0, I'm pretty darn close to 0 again for the voltage. So we're seeing something that's rather interesting, that when my angular velocity is high, my voltage goes negative. When my angular motion is negative, the voltage goes positive. And this is the quintessential show of Lenz's law. Remember that that a current is induced in the circuit so as to oppose the change in magnetic flux. So if my flux, and that's going through the area here, is getting bigger, the voltage is going negative. And when the magnetic field is decreasing, the voltage goes positive. So it acts in a very counterintuitive way that you would probably be best off seeing in a graphical representation such as this. Now let's do one other thing, because one thing we might want to do is determine the voltage as a function of the angular motion. Voltage as a function of the angular motion, and I claim that this is in fact linear. So let's go ahead. So what we're going to do is we're going to do a parametric plot. So here's my parametric plot button, and as you can see, I have gyroscope on the horizontal axis and high gain amplifier on the vertical axis. So now I am going to go ahead and shift this. Gyroscope is actually measuring the norm of all three components. I'm not so interested in that. I'm interested in omega y. The high gain, let's make sure we have everything correct. The high gain is voltage. So now what I'm going to do is I'm going to drag over this set of curves. And again, we see the pattern that I discussed earlier. It's 0 when the velocity is 0. It is negative when the voltage is positive, and it is positive when the gyroscope is at minimum, the voltage is at positive. When the voltage is at when the gyroscope is at maximum, the voltage is negative. So let's now drag over this, and you get this really funky looking bow tie pattern. I think you probably want to take some more data in order to get a fuller pattern. But here is what you see. If you look at the curve, there is a linear dependence between the voltage of the high gain antenna and the gyroscope's angular motion. So we have this linear dependence. Now what we would have to do is we'd have to take this curve and export it to a thing like Excel or Logger Pro, and then we can actually visit this data and maybe get a linear fit for it. And I will do that in another lesson. I've already run over time.